Hi, I'm Professor Melko, Chemistry PhD, and your chemistry professor. Today we're going to talk about exponential numbers and scientific notation. So let's jump into the lecture. Exponential numbers, you might have heard of these or used them before. It's just when a number is multiplied by itself. That's indicated with an exponent. So for instance, you can have 4 cubed. All right, maybe you're measuring the volume of a cubic solid where each side is 4 centimeters. You take 4 and cube that number to get 64 cubic centimeters. Sometimes you'll just express that instead of 64 as being 4 to the third power, right? Where the 3 here is the exponent, meaning 4 is multiplied by itself 3 times to get that number 64. This is read as 4 to the third power, or sometimes 4 cubed. When you use the power of 2, that's sometimes called squared. So 2 to the second power would be 2 squared equal to 4. These exponential numbers are going to be used in powers of 10 and scientific notation. Scientific notation is what scientists use to express really, really large and really, really small numbers. So powers of 10 are necessary for that, and a power of 10 is just a 10 to some exponent, right? So here 10 to the n means 10 is multiplied by itself n number of times, where n is going to be some integer, could be negative, like -2, could be 0, could be a positive number, like 5 or 10 or 100, okay? And this is going to be used in the following format. 10 to the 4th is 10 to the 4th power, or 10,000, okay? The shortcut here is the number in the exponent. 4 tells you how many zeros, 1, 2, 3, 4, come after the 1. Okay, so 10 to the positive 4 is a 1 followed by 4 zeros, or 10,000. Fun fact, Google, the word, means 10 to the 100, representing a really, really large number, kind of like Google represents a lot of information. So that's powers of 10. If the exponent is positive, like 10 to the third, it's a 1 followed by that many zeros, 1,000. 10 to the 1 would be a 1 followed by 1 0, or 10. 10 to the 0 would be a 1 followed by 0 zeros, so just the number 1. Negative numbers are a little different, right? 10 to the -1 are the number of zeros before the 1, so 0.1. 10 to the -3, there's 3 zeros before a 1, and the decimal is always after that first 0. So 10 to the -6 would be 6 zeros before the 1, and the decimal is always after this first 0. Right? To check, you can make sure you have to move this decimal place 6 places to make it the number 1. Okay, so that's positive and negative values of 10. Let's take a moment here. You can pause the video and try to write the following numbers as powers of 10, and the numbers down here out in their long form. The first one here, I'm going to write as a power of 10. I recognize it as a very small number, so I know it's going to be a negative exponent, right? When the zeros are before 1, this exponent's going to be negative. When the zeros are after 1, this exponent's going to be positive. Okay, the number of zeros before the 1 here, 1, 2, 3, 4, 5, 6, 7. So this must be 10 to the -7. The number of zeros after the 1 here is 9. So this must be 10 to the +9. Some students confuse this positive and negative exponent, but always have this check that a negative exponent is a small number, lots of decimal places, and a positive exponent is a very, very large number, lots of zeros before the decimal place. Writing the long form of the following numbers down below here, 10 to the 11 positive exponent. So I know that 11 refers to zeros after the 1. 6, 9, 11. So this represents 100 billion, or 10 to the 11th power. 10 to the -22, that negative means the zeros come first, so I have to write out 22 zeros. Yikes, that's a lot. I'm going to be here a while. Please hold. 9, 10, 20, 22, and then the 1 comes. And the decimal point is always after the first 0. Okay, so that's powers of 10. We're going to use this now to express scientific notation. And scientific notation is just the scientist's shortcut for expressing a number. So often in science, we use really, really big or really, really small numbers. So think about the size of an atom or the weight of an atom. mass of an atom, I should say, is really, 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 really tiny, right? Where the mass of the Earth, really, really, really large. And we don't want to write out, like I did back here, 22 zeros every time we just want to say a really small number. So we use scientific notation to express this really, really tiny number or a really, really large number. Okay, and it uses significant figures. So this is the sort of format of scientific notation. It's always a single number here represented by the letter D, followed by a decimal place immediately, followed by other significant digits. And that's why it's important to know how many significant figures there are in a given value or measurement. And so go back and review the significant figures video if you've forgotten that. This number of significant figures is then followed by times 10 to the n, where n is the power necessary to write out that big large number. Okay, so for instance here, this 93, there's two significant figures since the leading zeros don't matter, and I would write this as 9.3. Okay, all the significant digits, the decimal after the first significant figure, times 10 to the something, and you have to fill in and figure out what is this something, right? It's going to be a negative number here because this is a really small number and the zeros come first, and you count out the number of zeros there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So maybe I did that right, maybe I didn't, but 9.3 times 10 to the negative 23 is how I would write that number. Okay, so that's scientific notation. Place a decimal after the first non-zero digit, followed by the remaining sig figs, and then indicate how many places you had to move that decimal to get back to that original number. Okay, so here's some more examples laid out. This is the number of helium atoms in a balloon. Okay, I do the calculation and get this big, long, ugly number in my calculator. And maybe from my significant figure rules, I realize that I only need 3 sig figs. So I'm going to drop all of these extra digits and just write this as this big, long number with a bunch of trailing zeros. Okay, scientific notation says I write only the significant figures 2, 6, 8 and put a decimal place after the first sig fig there, and then times 10 to the, and you count up the number of places you had to move that decimal. Okay, for instance, writing this out, the decimal place was sort of implied to be here, right? 2, 6, 8 and a bunch of zeros, then a decimal places. How many places did I have to move that? 3, 6, 9, 12, 15, 18, 21, 22. So this must be 10 to the 22. Okay, you would report 2.68 times 10 to the 22 atoms. Okay, that positive power of 10 indicates I had to move the decimal to the left, right? That's what I had to do here, move it to the left. It became this positive number. Negative power indicates the decimal had to move to the right. So let's think about the length between a carbon and oxygen atom and a molecule of carbon dioxide. We breathe out carbon dioxide, and each of these molecules, the carbon and the oxygen, are separated by this many meters. All these leading zeros are not significant, so I know the significant figures here, if I need 3 of them, are 1.16. The rest of scientific notation always looks the same, times 10 to the some power, and now I need a power here. I know since there's a bunch of leading zeros here, this is going to be a negative exponent, right? I can count the decimal places to see how many places I have to move this. 3, 6, 9, 10. 1.16 times 10 to the negative 10, including the unit of meters. Okay. The other shortcut here, of course, is I can worry about, I guess not shortcut, but check that I can have, whether you're getting confused on if this is positive or negative in the exponent. At the end, when you have your scientific notation, think about it. A negative exponent, that should be a really, really small number. That's a really, really small number. If it's a really, really large number, this should be a really, really large number. Right? I should say if this is a positive exponent, this should be a really, really large number, which it is. So always have that check if you're getting confused with positive and negative exponents here. Okay, now you try a couple here. Pause the video, give it a shot, and then I'll solve them. The first thing we have to do here is worry about how many sig figs are there. 0.0500. These leading zeros are not significant, the trailing zeros after a decimal are. So there's 3 sig figs here. I'm going to record this as 5.00. Go back and review our rules for sig figs if that confuses you. So it's 5.00 times 10 to the some power. I have to move the decimal place 2 spots, so it's -2, right? And I know it's -2 because this is a small number, right? I know this is going to be a negative exponent. Okay. Likewise, I have to move the decimal to the right in making scientific notation, so I know it's a negative number. Right? In the next example here, 123,000, these trailing zeros are not significant, so I only have 3 sig figs. This is going to be 1.23 times 10 to the some power. If I move the decimal place to the left, 1, 2, 3, 4, 5, that means it's a positive exponent times 10 to the 5. And again, I have this check, 1.23 times 10 to the 5. Positive number should be a larger number. 123,000 is a large number. Okay, the last one here is a little bit tricky. 458 times 10 to the 4th, right? This you want to convert to scientific notation. It's not already in scientific notation because there's not a decimal point, right? Notice there's always one number, then a decimal point in all of these. Okay, so somehow I have to get this instead in the form of 4.58 from 458. So first I would actually write this out, or you can do it on your calculator if you want. 458, okay, times 10,000. You should get this number on your calculator, 4,580,000. That's 458 times 10 to the 4th. Now I'm going to assume the decimal place is here and see that I have to move it 1, 2, 3, 4, 5, 6. 6 places to the left. That means it's a positive 6 exponent. And so this should be my final answer here, 4.58 times 10 to the 6. Okay, so look out for these tricky examples. But other than that, it's pretty straightforward. You have to do enough practice problems till this becomes second nature, because this scientific notation is used in all of science and really important for all the work we're going to do in the rest of these videos in this course and in science in general. So that's it for this video. Feel free to subscribe on YouTube, catch my office hours on Twitch every week, and watch the next videos in the series. See you next time.